So today I'm going to spend most of the time trying to make you understand the definition of a matrix in row echelon form. So definition of a matrix that is in row echelon form. And the matrix in question can be quite general. It need not be a square matrix. It can have more columns than rows, or it can have more rows than columns. So we will take an example where in the picture, it will look as if it has more columns than rows. Okay, so take a M cross N matrix. So M and N are integers, non-negative, greater than or equal to 1. So each of them must be at least equal to 1. Otherwise, there's nothing to discuss. And so take a M cross N matrix A. So when is it in row echelon form? So it has the following shape. I'm just reading from the notes. So it has M rows and N columns. And in the picture, it looks as if there are more columns than rows, but that is because, that is the way I draw the picture. It need not be the case. M could be equal to N, M could be less than N, N could be greater than N. Okay, so when is an M cross N matrix in row echelon form? It has the following shape. Okay, I will write it down. So I'm not going to give a precise definition yet, but we will come do that soon. Okay, it has the following shape. So just let me just write it like that.
Excuse me, sir.
Just, yeah.
Yeah.
What's the problem? Sorry.
Sir, actually told me to remind a problem that was not addressed in the previous class.
Yeah, tell me.
Sir, it was about vector spaces. I mean, distinct vector spaces being when the entire vector space is the direct sum of v plus and v minus.
That old problem.
Yeah.
Yeah. Okay. So this is the wrong time.
This after the class also, if it's fine with.
Right. Just 1 second.
Yeah.
Yeah. Yeah, we'll have to do this later. Yeah.
Okay, sir. Thank you so much.
Yeah. I need to spend some time on this because there are a number of points that you have to understand. So you can only understand it with a large enough matrix. So that is why I'm.
Yeah, sure, sir.
I forgot something here. Okay, so it has the following shape. So what do I mean by the following shape? So now let me just set out the rules. When is a matrix in row echelon form? So here are the rules. One, in each row, the first non-zero entry reading from the left is one. Is by one I mean is the number one. Now, if a non-zero entry exists, so I should say this. So each row, if either all entries are zero, either all entries are zero, or okay, so in fact, let me just make the change in the notes just to be very clear. This not this entry, this this location is called the pivot. So pivot is a point on any device around which you can rotate the device. So it's sort of you pivot. I don't know if can you see me? Yeah. So for example, if I keep my hand on the iPad like this and I move like this, then the point where my thumb touches the iPad, I'm pivoting. That is a pivot. Okay. So that's the meaning of a pivot in English. So if you go down from the top, and so this is a way you should approach a matrix to see if it's in row echelon form, go down from the top row and inspect each row. If either the row is entirely zero, so let me put such a row at the bottom here. That may or may not happen, but so here is a row with no pivot. So there is a reason I'm putting that row at the bottom. That will become clear when I give you the other rules of recognizing matrix in row echelon form. Okay, but the point is, the first 4 rows in this example, there is a pivot. In the first row, it is the third. It is here. It is in the third place. In the second row, it's in the 5th place. In the third row, it is in the 6th place. In the 4th row, it is in the 9th place. And each of those, the first non-zero entry in the row is equal to 1. That's the first rule of a row echelon matrix. The second rule is that the entries above a pivot are 0. So look here. Here are the pivots. So this was a pivot. There is no row above that, so there's nothing to do. This is a pivot, and then here is one possible entry, and that is 0. Here is a pivot. There are two possible paired places above it in the array of the matrix, and the entries are 0. The next pivot is here, and all the entries above are 0. Now, there need not be a pivot in every column. So for example, the 4th column here, which is this one, has no pivot. This column has no pivot. This column does not contain any pivot. Okay. So this entry, which is to the right of a pivot, and there are no pivots in the corresponding column, can be anything. Similarly, these entries, which are, so this is to the right of this pivot, this is to the right of this pivot, this is to the right of this pivot, and there is no pivot in this column. So these guys can be arbitrary real numbers. And similarly, these guys. Third, so this is the sort of the most curious or subtle thing. If the ith row has a pivot, then either one of two things happens in the next row. All the entries in the rows below the ith row are 0, or the I plus 1th row has a pivot, which is to the right of the pivot in the ith row. So let's go back here. So you see, so in other words, the shape of the matrix must be that there are a certain number of rows which can be, rows with no pivots. So let me write this more carefully, more clearly. No pivots. And then the rows above, each row has a pivot. And the pivot in the, if there is a pivot here, then in the next row, the pivot must be to the right. Okay. So these are the conditions which, if all these conditions are met, the matrix is supposed to is said to be in row echelon form. Okay.
Sir, but is it necessary for the I plus 1th row to have a pivot? I mean, if ith row has a pivot, and then either
if the I
all
plus one, if the I plus 1th row does not have a pivot, then all the rows below the ith row are zero.
Okay. Sir.
Yeah. Got it? Yeah. So yeah, so let us, first of all, let me give you enough time to internalize the definition of a matrix in row echelon form. Okay, so let us see how we can build up a matrix in row echelon form. Okay, so you start with matrix like this. So there is a one, start with a 1 here, then in the next row a 1 here, then in the next row a 1 here, and this is the last row with a pivot. Yeah. Sorry. This is not the full matrix, but 0, 0, 0, 0, 0, 0, 0, 0, many rows. Okay, you come here, you get up till here, and then you add more rows with zeros. As many as you want, maybe none. And it may extend beyond this. And then what you do, you fill up these entries. I've not drawn this carefully enough. So let me draw this more carefully. And here it can be anything. So all the blue things can be anything. So this is how you, this is one way of visualizing metrics in row echelon form. Maybe this is not helping. I think I will just remove this. Yeah, I think it's best to stick with the definition and try to get used to this. I don't know why it's not letting me delete it. Okay. Any questions? Hello. I mean, I have not yet said what we are going to do with matrices in row echelon form, but I have defined the notion of a matrix in row echelon form. Neelabja, it's okay?
Sir,
Yes, sir.
In place of stars, zero can also occur.
In place of where?
Stars.
Star,
Like,
any real number, including zero. Yeah, thank you. Yeah.
thanks.
Yeah. Any other question? Okay. So we will practice with small examples how to get metrics in row echelon form. Any reasonable mathematical software will let you do this. And I think there are even online things which will automatically tell you how to bring a matrix in row echelon form. If you feed in the matrix, it will spit out the corresponding matrix in row echelon form. So what do I mean by that? So I am jumping ahead of myself. So here is the main result. Theorem. Any M cross N matrix A can be brought into row echelon form by a sequence of elementary row operations. So I mean, I will explain what that means. Equivalently. So let me just, so we will see why this is equal. So the point is, I'm going to write the theorem and then explain what this means and the connection between this phrase and this. Equivalently, there exists a sequence E1, EK, EK minus 1, E1. So there is a reason I am writing the sequence in reverse order of elementary matrices such that A prime, which is by definition, EK into EK minus 1 into E1 into A is in row echelon form. So this theorem I have stated in the order in which I want you to remember it. A more logical way of saying this is that given any matrix A, there exists a sequence of elementary matrices such that when I take A and multiply on the left by first E1, then by E2, then by E3, and then at EK, the resulting matrix is in row echelon form. Okay. Now, so equivalent, why is this equivalent? Well, so it is equivalent because, so I have to explain what are elementary row operations on a M cross N matrix. Well, there are the following kind. First type, and so let me write the matrix like this. A is first row, second row, mth row. First kind, A goes to R1, I plus A J Rn, where A is a real number. Second kind, R1, Rj, Ri, so Ri and Rj get interchanged. Third kind, so this is the second kind. The third kind so this is the third kind. So what the theorem says is that I can start with A and do a sequence of such operations, namely for a suitable A and suitable I and J, add a multiple A times the jth row to the ith row, and the other rows don't change. The second kind is exchange the ith and jth rows where I and j are different indices. The third kind is pick a row, say called the jth row, pick a non-zero scalar C and multiply that row, every entry in that row by C. So because of what I have explained this part. And why do I say that this equivalently means that this part is equivalent to this part. And that's because in the last lecture, I explained why multiplying a matrix on the left by an elementary matrix of the first kind, second kind, or third kind corresponds to what we just described as a row operation of the first kind, second kind, or third kind. So you should, after all this, at least understand the statement of the theorem. We are not going to prove it. In fact, even Artin doesn't prove it. I think the proof is not difficult, but it is somewhat tedious and involves bookkeeping, and you don't need to know it. And I mean, of course, if you are interested, you should certainly read the proof. Now, the point is, in actually practical computations, my understanding is that if I remember right, you can make this into an algorithm, but it is a quite an inefficient algorithm is what I seem to remember. Let me just check this. This is an important, see, whenever you deal with matrices, it's really important to ask, whatever I do, can I do this using computers, because that is where they are really important. Let me just check. Okay. I'm finding there is a fair bit of, it is a really important algorithm, but if I remember right, I think you should try to avoid using the algorithm, because it is not a very efficient algorithm. So yeah, I will confirm this to you later, just as a matter of curiosity. Okay. Now, the other thing you need to remember is that I'm not saying no uniqueness is being claimed. So note, we are not claiming that the sequence ek minus 1 e1 is unique, not even k. Okay. So different people may find different numbers of elementary transformations, and the transformations may themselves be different, but the row echelon form corresponding, so call that A prime, corresponding to a matrix A is unique. So given any matrix, regardless of which sequence of elementary row operations you choose to do, you will end up with the same end result A prime in row echelon form. So there is a well-defined map from the space of all m cross n matrices to the space of m cross n matrices in row echelon form. This is not a continuous map in any sense, but it is a well-defined map. Okay, so I think that is the end of our theoretical discussion about row echelon form for today. There is one other conclusion that we can draw from this. I'm not sure if I should do it today, but I will just put it up because it's a very important fact, important consequence. If m is equal to n, then so yeah. Square matrix A is invertible if and only if corresponding row echelon matrix A prime, so n cross n, is m cross n, is the identity matrix. So if you take a square matrix and reduce it to row echelon form, one of two things can happen. It is, if the original matrix is invertible, then the row echelon form will just be the identity matrix of size, of that corresponding size, or the matrix is not invertible, in which case you will end up with a row echelon matrix which is not invertible, which should mean that it will have at least one row at the bottom consisting of all zeros. Okay, so this is an important consequence of all that went before. So this is something that we will come back to and actually prove, but assuming the main theorem, namely that any matrix can be brought into row echelon form by elementary row operations. Okay, we will assume that, and then we will prove this.
Sir, will we be proving the uniqueness?
Sorry?
Sir, I mean, will we be proving the uniqueness of the row echelon
No,
form?
I will not be proving that also. Yeah.
Okay.
Yeah. I will not be proving that.
Excuse me, sir.
Yeah, in fact, I will be proving very little regarding this. Yes, another question?
Yes, sir. So, sir, we defined elementary matrices to be like three different forms. So, if we have every element multiplied by k, will that also be an elementary matrix?
Every element of a matrix.
No, every element of the elementary matrices we already defined.
Right.
If we multiply them by k, will that also be an elementary matrix?
Well, what do you think? So take one of the examples. Take the example of the matrix that flips two rows.
Yeah.
And supposing now multiply every entry by say 2.
Yeah.
Okay. Is that an elementary matrix?
But then Yeah, it's not strictly an elementary matrix.
No, so it's not.
Yeah.
Okay.
Okay.
I mean, there is no strictly about it because the definition of an elementary matrix is very specific.
Okay. Yeah.
But so the answer to your question is no, clearly.
Yes, sir. Yeah.
Yeah. Because see, the point is that most entries of an elementary matrix are 1 or 0.
Yeah.
Okay. So if you multiply such a matrix by, say, 2, the 0 entries will remain 0, but the entry 1 will become 2. And that is not an elementary matrix.
Yeah. Okay, sir.
Yeah.
Yeah.
Sir?
Excuse me, sir.
Yeah.
Sure, go on. Sir, I had a
Yeah.
doubt about. Okay, let me ask first.
Yeah.
So I had a doubt about this row operations. I mean, is it a convention or there's a reason why we only do row operations and not like column operations?
You can do column operations also. Yeah, definitely.
Okay.
You could do, I think you could repeat the whole thing with column operations. My understanding is that for all I know in computational linear algebra, which I keep telling you is very, very important, but which I have studied very little, you may have to combine the two. Okay, but the theory will be very parallel. Whatever I say, but let me ask you, how would you implement a column operation using elementary matrices? What do you think?
So by multiplying it on right of the
Exactly. So if you take a matrix and multiply it on the right by elementary matrices, remember, if you are looking at m cross n matrices, then for multiplying on the right, I'll have to look at n cross n elementary matrices, not m cross n, not m cross m, because elementary matrices are square. So for multiplying on the right, I'll have to look at n cross n elementary matrices, and you're absolutely right. If you see what multiplication on the right does, what it does is elementary column operations, namely exchange two columns, add a multiple of one column to another column, and multiply some column by a non-zero scalar. This is something that you can yourself check.
Okay, sir. Thank you.
Yeah, but then then you will get the standard form will not be in row echelon form. It will be something else, which I don't want to talk about. I mean, yeah. But since you asked, you should think about it. I think it's a good kind of yeah.
Yes, sir. Okay.
Yeah. So I think there was another question.
Yes, I have a question. When you talked about a mapping from a matrix to its row echelon form, you said it's not continuous, right? I don't understand what continuous mapping means.
No, well, so the space of, say, take an example of M and N, okay? Take 2 by 2 matrices, okay? So 2 by 2 matrices are, there are 4 entries. So 2 by 2, the space of 2 by 2 matrices is R to the 4, right?
Yeah.
Yeah, it's a 4-dimensional vector space with a basis, so I can identify it with R4. Is that clear? So all I'm saying is that we call this M2 cross 2. That's a vector space, and it is a vector space that's isomorphic to R4. So there is a I can talk about continuity. You do when you did multivariable calculus, you considered functions on real vector spaces, and you asked whether they were continuous, even differentiable. Oh, I forget, you're first year students. Okay, yeah. So sorry. So the point is, because it's the space of matrices is like R to the n. Any function from that into any other R to the m, you can ask whether it's continuous or not. right? Because are you learning continuity of maps between metric spaces, right? In your other course, analysis 1.
Not yet, sir. No.
Okay, but think of this. This is not very fancy. You are looking at maps from R to the M into R to the N, so that clearly at least you have some intuitive understanding for when this map is continuous. When I change the point on the left, namely if I change the input metric slightly, that means changing each of the entries a little bit. The output metrics should not change too much. So that's what continuity means. Okay.
Yeah.
So now think of, can you guess why this row echelon form thing is not likely to be continuous? That's because, when you if the first entry, okay, this is an exercise. Yeah, thanks for asking this question. But just try and think about this. We can revisit this tomorrow. In the next class. My point is that if I change, I start with A and I have an A prime. If I change A slightly, the output A prime can be very different.
Okay.
Yeah.
Thank you.
So one more thing. So for a system of equations, this is also related to the proof of there is no direct injection from R to the power n1 to R to the power n2 where n2 is greater than 1.
You can use this to do that. Yes. Yeah.
Okay. Yeah.
Yeah. In fact, if I remember right, Artin's proof does so. The proof that I postponed will go through this. Yeah. So in fact, that is something on the agenda. You remember when I proved that the dimension is well defined, that leaned on the fact that any map from R to the N to R to the M has a kernel if N is bigger than M. And I have not actually proved that. I postponed the proof of that. And in fact, we will use this row echelon business to prove that. Yeah. Any other question?
Sir, actually, I have a doubt.
Yeah. Who is this, by the way?
So this is Srivani.
Yeah. Okay.
So like the first row of a row echelon matrix can be all zeros and the second or the third row can have a pivot, right?
No. If the first row is 0, then everything below is, because, the pivot in the I+1th row must appear strictly to the right of the pivot in the ith row. So if there is no pivot in the first row, there cannot be a pivot in the second row.
Okay, sir. Thank you.
Yeah. So if the first row is 0, then the matrix is identically 0.
Okay, sir. Thank you.
Yeah. Any other question? Very good. So what I want to do now is basically let me now, should I stop recording or not? Because now I'm going to kind of sort of, what I want to do is to do an example, which I have not prepared. So it will be, it can get quite ugly. Let me do the following. I will stop the recording, take a break. But before I do that, let me at least present the metrics to you so you guys can think about it. Okay. So the rest of the lecture, we are just going to work out one example of a matrix A and then try to get it into row echelon form. So this is exactly, remember that this row operations on a matrix are just an abstract way of whatever you used to do to solve equations. So one will do a similar thing. So let's give me a simple example of a matrix that we can practice on, and then I will leave you with that. Okay. So example of A going to A prime. So let me take simple examples that we can actually do within a reasonable time. Let me do 2, 1, 1. 1, 2, 3. 1. 1, 1. So this is actually a square matrix. So maybe that may not be so smart, but anyway, so let me leave you with this, and I'll take a little break, and then you guys can kind of play with this. So what is A prime? What is the row echelon form of this? I hope, yeah, it should be doable given in about 20 minutes that we have. So I'm going to, yeah, let me just